condition mark.
Okay, it's on. And I'm not quite sure about this. This is on.
Yeah.
This is just turned on.
Okay.
It's 27, maybe a little bit lower.
It's okay. So I close the window.
Yeah, please. And maybe the back door. Can we turn off the front row of lights? The first row. There we go. Okay, hi, Jingyuan. Good to see you. Okay, the primary goal today is to finish chapter 3. Okay. 诗为言详书语. Yeah, the usual suspects watching the videos from remote locations. Okay, good. So let's go over the announcements. Oh, by the way, today, this week is the exam week, so we'll be having exam 3 on Thursday, which I don't think that I need to say it again. Something that's slightly new this week is that there are 2 quizzes due this week, 24 and 25, and potentially 26 and 27, depending on how fast we go. All right. Oh, wow. Okay. Jingxiang, Ethan, and Yuze are all here. Great. Yeah, so this is where we were last week when we finished. So we actually finished talking about the EIMD mechanism, as well as the separation of startup state versus steady or congestion avoidance state. So the finite state machine of TCP's congestion control mechanism. Hello? Oh, okay. The finite state machine of the TCP's congestion control mechanism is actually not that complicated, essentially 2 states, slow start state and congestion avoidance state. And to trigger slow start state to go to the congestion avoidance state is what? When the window size exceeds the SS thresh, the slow start threshold. Now, if we look a little bit closer in each of the states, you see there are these, to come back to the slow start state, if we run into a timeout, window size will be reduced to 1, right? Then it's like working in the slow start state. And we see that in both of the states, there are these transitions that's triggered by new ACK. Okay, so this is a successful data transmission, triggering the receiver to send a new ACK. So what we do there is what? Increase the window size. But the amount of increment is a little bit different depending on whether we are in the slow start state or the congestion avoidance state. What are the differences? Over here, upon each ACK, we increment the window size by 1 MSS. But here, it's actually 1 over the whole window size, okay, MSS. So to be exact is MSS multiply MSS divided by CWND. All right. Now we also see transitions triggered by timeouts, okay, in either case. So in slow start case, if it's timeout again, simply set the window size back down to 1. In congestion avoidance state, when there's timeout, set the window size back to 1, which is like starting from the slow start state. Okay. So there's no differences depending on which state it is. But make sure that the duplicate ACK is reset. The count is reset to 0. Speaking of duplicate ACK, in both states, we also have the transitions triggered by receiving 3 duplicate ACKs, don't we? And the operations are actually identical in either. So threshold is half of the congestion window size. Congestion window size is exactly the threshold. And then we reset the duplicate ACK counter. In the meantime, retransmitting the missing segments just like in the timeout transitions. All right. So new ACKs are the transitions sending the new packets. Timeouts, meaning packets are lost. So changing the window size, and in the meantime, retransmit the missing packets. Dup ACK, 3 duplicate ACKs, also some packet is missing. Changing the window size, in the meantime, retransmitting the packets. All right. Now, otherwise, if it's just receiving a duplicate ACK, but the count is not yet 3, we simply increment the duplicate ACK count by 1. So, sounds simple. And we actually started working on a what? A quiz number 23. It turned out that in the congestion avoidance state, the way we are incrementing the congestion window size is a little bit tricky. Okay, and okay, let's walk through it. Okay, again. So the question was, okay, we do have 2 hosts, right? A is sending data to B, B is sending ACKs back to A. And the scenario is this. Initially, the window size at host A is 4 MSS. Threshold, A. Now, in Q1, assuming A being A MSS, there's no issue, no problem, right? Because B here is obviously going to be incremented by 1 because 4 is less than 8. So B will be 5, right? C will be 6. And D, oh, wait a minute. D here says the ACK here says 2 MSS. This is already a duplicate ACK. In terms of duplicate ACK, where the duplicate ACK count is not 3, we simply increment the duplicate ACK count and do nothing about the congestion window size. So D here remain what? 6. The question is this for Q2. What if A is 4? When A is 4, oh, wait a minute. When the threshold is now 4, we exit, right, the slow start state. So the increment should be, MSS multiply MSS divided by CWND. So what will be the value of B then? Don't worry, okay, because last week I kind of promised that I make sure this is clear. So let's focus on Q2, okay, where A is 4 MSS. Let's now calculate B. B should be this, right? Because we're now in congestion avoidance state. So congestion window size plus, according to the formula, MSS multiplied by MSS divided by CWND. All right. And currently, CWND is 4. Therefore, we substitute by the CWND by 4 MSS. 4 MSSs. All right. So what is the right term? The term on the right? So you see the MSS crossing out with this other MSS, okay, above, below the divider. So this is just 1 over 4. So the term on the right is going to be a quarter MSS, right? So together, 17 quarter MSS. And if we use a calculator, it should be about 4.25 MSS. Now, there was a question from the class asking, then if the window size is now 4.25, how many packets do we send next? Can we have like a fraction there in window size? Yes, we may. As to how many packets we send further, it really depends on the data size. Okay? So if we have very many small data, a small amount of data to send, we could actually send like 3, 4, 5 packets as long as the sum of the bytes is below 4.25 MSS. Okay? So the number of packets we can send next really depends. Okay? Depends on the application. But if we assume that all the packets to go out needs to be in maximum segment size, then we can only send one because 0.25 is not big enough to send a whole big packet, right? Good, so I hope that is clear. Oh, by the way, even though at the time point we received the first acknowledgement, we could calculate the condition window size to 4.25, but we are not quite sure how many packets we should be sending out. But that doesn't stop us from calculating the condition window size C, isn't it? So C is when we receive ACK for packet 2, MSS. So let's apply the same technique. C should be the current condition window size plus MSS divided by CWND. Let's substitute CWND with the current window size. What is that? We just calculated it, right? 17/4. There we go. So the second term, let's cross out the MSS. So it's going to be 1/17 MSS, like this. The thing is that if I, again, use a calculator to get it to the numerical value, so it will be about 4.45 MSS. That is about what? 4.5. So there was a student in the class saying, hey, I'm guessing 4.5. I didn't even bother, right, doing the exact arithmetic, but it should be about 4.5. Okay, the student was correct because the idea is that after one round trip time, after 4x, we increment the window size by 1 MSS. Therefore, right, approximately 2x should get it to about 4.5. We're very close, okay, about 4.5. All right, so I hope that the way we're incrementing the window size in condition avoidance state is clear. Okay. Oh, oopsie. Okay, well, you see the next quiz. Okay. Let's now continue on to the lecture. So this was the finite state machine, okay, of TCP's congestion control. Okay. Just like in reliable data transfer of TCP, what we did there is we also tried to improve, for example, the retransmission delay. So there was like a fast retransmission mechanism there. In order for TCP congestion control to react a little bit faster in case there are loss, there's also an improvement called fast recovery. Okay. That is also saying that the finite state machine of the congestion controlling TCP is not as simple, unfortunately. Okay. And the part being changed are these. The 3 duplicate ACK transitions. Originally, when TCP sender detect there are 3 duplicate acknowledgements, oh, okay, cool, then we should do fast retransmission, right? and treat it as a packet loss, dropping the window size to half, okay, and then retransmit the missing packet. In fast recovery, okay, so these two transitions are changed. In fact, okay, it's changed this big. So in either case, either slow start or congestion avoidance, when there are 3 duplicate acts, we all trigger and move to the fast recovery state. So you see the 3 duplicate act here and here will take us down to the fast recovery state. And the difference is actually in the red circle. We changed the SS thresh to half the window size. Previously, we changed the window size to SS thresh, but now it's what? SS thresh plus 3 MSS. So it's a little bit more generous, isn't it? So let's not be so strict, dropping it to half and starting from there. Let's drop it to half the window size plus 3 and start from there. Okay. And then we're now in the fast recovery state. Know that, hey, there are some new transitions. First is this. Oh, in the fast recovery state, if we receive duplicate acts, what happened is this. The congestion window size is incremented continuously. If there's one more duplicate act, increment the window size by 1. If there's another, increment the window size further by another. Okay, MSS. Can this really be happening? It's actually possible when the original window size is already large, okay? And right at the beginning of the window, there's just one packet being delayed longer, then you could be receiving quite a few duplicate acts, not just 3, maybe 4, 5, 6, okay? So if you recall quiz 23, right? Originally, at the beginning, sending 4 packets. What if we are sending 8 packets at a time? Right? And packet 3 is lost, then you're going to receive lots of duplicate acts. On the third one, we go to the fast recovery state. For the 4th, we're going to continue increasing the window size by another 1. So this will go on until 2 cases. On the left, timeout occur, or on the right, receiving a new acknowledgement. Okay? Either case will take us out of the fast recovery, okay? The worst of the 2 cases is what? Timeout. In case of timeout, we will go back to the slow start state. Window size back down to 1, pretty much the same thing, and then retransmission. When there's a new act, look at this. Congestion window size is actually set to threshold, which is restoring to half of the original window size before 3 duplicate acts. So these extra MSS given, okay, during the fast recovery is now removed. So window size will be dropping back down to half the window size before 3 duplicate act. Okay, resuming to normal. So fast recovery is just a state for the cases where we have large window size to begin with, okay? And within a flight, one of the early packets get lost or delayed. Okay, so the dupe act count is finally reset here, meaning exiting the 3 duplicate act state entirely. Okay. All right, so this now is finally the complete FSM of TCP's congestion control. So in total, we have 3 new act transition and 3 timeout transition. Okay. But of course, there are 3 duplicate ACK transitions as well. So up here, down here, and another one here. Okay. The only transitions remaining in having only 2 is just this dup ACK count equals 3 here, and another one here. Yeah, it does look a little bit weird. Okay, let's exercise it with another quiz. Okay, number 24, let's bring it up. So this is fast recovery. So I also show the state machine there. The scenario is actually the same as quiz number 3. Okay, what's being added more is simply here. Look at this. Okay, after receiving ACK 1 MSS, B will be recalculated. Okay, and 1 packet is sent after that. After receiving ACK 2 MSS, C will be calculated, and another packet is being sent. Now, ACK, the second 2 MSS, when it arrives at host A, because it's a duplicate ACK, we only increment the counter by 1 and do nothing. Okay, so window size is not bigger, and if there's no triggering from the application layer, there's not going to be more data going out. The thing is that, hey, the ACK for these 2 additional packets are going to come back. What will be the ACK number there? It would remain 2 MSS, isn't it? So this is first duplicate ACK up here, the second one here, the third one here. So 3 duplicate ACKs is going to what? Oh, trigger something. So Q1 is asking, if let's assume that this is the original TCP congestion control of finite state machine without fast recovery. Okay, what will be the value of E and F? Anyone? It's quite straightforward, isn't it? Okay. Oh, of course, we know already, right? The value of D is 4.49. So what should be the value of E? Wei Yao?
The value of D divided by 2.
Exactly. Value of D divided by 2. And the value of F?
Without fast recovery will be the same as.
Great, great. So with fast recovery, what do you say? E will be the same? Would E be the same?
No, E will be the value of thresh plus 3
E or F? E is the threshold. Oh, okay. You guys are probably looking at a different printout. On Slack, right? I see, I see. So if E is the congestion window size, you're right. Okay, I should actually change this, sorry. Let me change the slide here so that it's not confusing to you guys. I think I had it reversed. F and E like this, right, on Slack. Is that right? Good. Yeah, so this way there's no confusion. So E will be D divided by 2 plus 3. Do you all have the same answer? Very good. So let me just take a note here. I think there you go. So you're done with Q24. Good. All right, so I guess fast recovery is not that hard to pick up. Okay, and let's close this and move on. There we go. Okay, now we're in these. So fast recovery, done. There are just two more issues about TCP we need to cover. Okay, so these are actually more advanced. It'd be interesting to know. First is TCP is not very good for this type of connection. Very long connection and connection that demands really, really high throughput. Okay, so let's consider this example, this scenario. Assuming the packet size is 1500 bytes, round trip time 100 milliseconds, and our goal is to achieve 10 gigabits per second. So think about this being a TCP connection used by Google to synchronize the data in their data centers. So we know already, right? The transmission rate of a TCP connection is essentially this: congestion window size divided by the round trip time, because amount of data we send within a round trip time is about this big. Okay. Now, if we want to achieve 10 gigabits per second with, so 10 gigabits per second substituted here, round trip time is 100 milliseconds, then you get this, isn't it? The congestion window size needs to be this big. 83,333 segments. Do you see a problem here with really, really high number of packets in flight? The sender sends packets, but can the sender just leave the packets alone after they send? They cannot yet. They actually need to keep these packets until the acknowledgements for these packets arrive, isn't it? So 83,332 packets can be in flight, meaning the sender needs to have enough buffer space to keep 83,333 packets of 1,500 bytes long. How much memory is that? Well, a lot. 33 bytes, megabytes, in fact, at least. Wow, just to keep a TCP connection? That much memory? The receiver is not better either, right? Receiver now also buffer out of order packets in TCP, isn't it? So potentially you might need to also have that much memory. 83,332 packet large memory space for just one TCP connection. Yeah, so TCP with the transmission rate designed this way is not very good for long, fat pipes. And this is, in fact, already ideal. Look at this. TCP is not without loss. If there's loss, the transmission rate is even lower. So this is considering loss. Okay? As a result, you see the behavior more like this. Okay? Without loss, just keep increasing linearly. If there's a loss, you drop to half. Okay? And so on and so forth. Okay, so that's assume the average window size at the point detecting an error is W. Okay. Then you see this sawtooth, really nice, pretty sawtooth behavior going on and on. The average TCP throughput, okay, is in fact this. 3/4 of W over RTT. Not quite, just W over RTT. Oh, by the way, I changed the notation. So W here is essentially CWND, okay, the window size. But this W is the CWND when there's a packet loss, a 3-duplicate packet loss detected. 3-duplicate kind of loss detected. So this is a very ideal case again. Okay, so ignore the soul star stay. Okay. So it's in fact lower. So more packets need to be in flight. Now we don't have time to go through it, but if you look into this technical paper, the authors actually derived TCP throughput, the average TCP throughput, and represent it not by just the window size and RTT, but also by the loss rate. Okay. And one can actually plug in the scenario we had earlier. Packet size, round trip time, and the throughput we are looking for. And discover, oh, the loss rate needs to be super low. Okay. So in a way, to support really long, okay, with 100 millisecond round trip time, and fat pipe, meaning really, really high throughput, we need to have a lot of memory space at the sender and receiver. We also need to make sure the network, okay, will not give us a lot of loss, a lot of error. Well, having lots of memories at the sender-receiver side might be a little bit more doable, but it's really hard to control the network such that the loss rate is this low. Okay. So you see that there's need of reinventing TCP so that it works for these long fat, long big pipes. So that's one major issue in TCP today. Another issue, fairness. Okay. So ideally, okay, let's say that if we have KTCP connections sharing a common link with bandwidth R, then each should get R over K share of the bandwidth, isn't it? So this is considering fairness between the TCP connections. So look at the scenario below. Okay, the bandwidth here is R. If there are two, each of the connections should get what? A half R. But with the TCP's rate control mechanism, window size control mechanism, give us always something like this. Okay? Two concurrent TCP connections, eventually getting half of R. Well, the answer quickly is yes. But why? How? Okay, so let's use this plot here to figure out. And so that you see, eventually, the multiple connections running simultaneously sharing the same link is going to give you fair throughput. So on the x-axis, this is representing connection 1's throughput. Okay, down here. Y-axis, connection 2's throughput. Now the link has only capacity R. So you see that the blue line here represents what? The capacity, isn't it? If connection 1 has R, then connection 2 must have nothing. Okay. If half R, the other one, half R. Or if connection 2 having R entirely, then connection 1 gets nothing. Okay, so the blue curve is like the capacity limit. That is also saying the state of connection 1 and 2, if it goes beyond blue line, like to the upper right, then expect packet losses. Because this is beyond capacity, chances high the packets will begin to drop. Towards lower left, okay, there's more capacity, chances high that both connections will continue to increase the window size. Now the true fairness is right here, right? When both connections have the same amount of bandwidth. And the ideal case is right here, right? Each of them gets 1/2 of R. Now, connection 1 and 2 can be starting at different point in time. Okay, let's assume that the connection 1 starts a little bit earlier, therefore having a higher throughput to begin with, and connection 2 slightly lower. Okay. But the thing is that as these two sessions go on, when it's below the blue line, okay, both of them will additively increase the window size, but increase at the same pace. So the increasing trend will be what? A linear slope 1, like this. So come down here. So this is the starting point of the observation. Connection 1 has this much bandwidth, or this much throughput. Connection 2, only very little, a small amount. Okay. So this is below the blue line, so they will both linearly increasing the throughput. But once going beyond the blue line, here is the region packets will begin to drop. And so you see this. Both connection dropping packets, each of them drop to half of its original throughput. So you see, connection 1 dropped from here to here, which is half of the whole thing. Similarly, connection 2, this is the whole thing, and dropping to half of that. And now below the blue curve, they will grow linearly again like this. And packet drop again, dropping to half of each of the throughput, and on and on. What do you see there? Yeah, they're actually converging, approaching the fair line there in the middle. So you thought, EIMD, why? So weird. It's actually designed for the purpose. Okay, for the long run TCP connections, eventually achieving fairness to each other. So there'll be not like, if I start first, then I get more throughput. And then I'll be hogging to the throughput, hogging to the bandwidth, okay, and not releasing it at all. Okay. So you can probably see the value of doing the multiplicative decrease. That was the trick. All right, and that also takes us to the next quiz. So this was the quiz. Number 25. So using the same plot, can you tell me, okay, would the two connections throughput converge to equal bandwidth? Okay, if the congestion window size is adapting, okay, in a very different fashion. Q1, what if the congestion window size is adapted this way? AIAD, additive increase, additive decrease. Q2, what about MIMD? Oh, multiplicative increase and multiplicative decrease. And what about the last one, Q3? MIAD. Okay, so talk to your teammates. AIAD? Would it work? What about MIMD? Last one, MIAD. So what do you think, guys? Oh, okay, so I see. Sure.
The AP means that if loss happens, it will cut one.
Yeah, the same way it's being increased.
Oh.
So essentially a constant. Oh, I hear you. Q1 seems to be straightforward, isn't it? But what about Q2? EIMD. Hi, hi. Yeah, yeah. A constant. Are you ready?
I think 1 and 2 will not make
Fair.
fair.
Okay.
Because the AIAD is at the client is 1.
Linear increase. Slope 1 increase.
MIMD, I think it is the line connect it to the 0, 0, and it will move on this line only.
MIMD or MIAD?
MIMD.
MIMD, okay.
For the MIAD, I think probably yes.
Probably, okay. Interesting. Any alternative thoughts? That was James. Okay, Q25.
I think MIAD will not be a fair, because if you look at the figure which is quiz 25 and put the arrow upside down, it will go outwards.
It will go out, not converging at all. Ah, okay. And I think you're Boschin, right? So team 4 here, back to be different. James?
Maybe I should change my answer for question 3. I think MIAD will make the unfair more and more.
Yeah, so Boschin is saying similarly. Think about it, guys. So if we do MI, multiplicative increase, what's going to happen? If we do MI, what would the curve be like? Right? If we do AI, it's a linear slope 1, right, over time. If it's MI, what do we do? Oh, so bandwidth for connection 1 is doubled. Bandwidth for connection 2 is also doubled. which one grow faster? Still, right? The early start connection grow faster. So it's going to be so if we start from the same point in the example we saw earlier, where connection 1 has a bigger throughput to begin with, connection 2 a smaller throughput. Let me use the whiteboard. So this is the limit. This is the fairness, right? What if we start here? Connection 1. Having a bigger throughput to begin with. Connection 2, small bandwidth, right? Connection 2 bandwidth, really low. Connection 1 bandwidth, much higher. So this will double. Oh, extend here. This will also double, but extend only here. And so the curve is going to look like what? A log curve, a sublinear curve. But the Bo-Shin and James also thought about, hey, what if here, right? If this is the point we start with, we go what? Exponential, and maybe more. Oh, it's not really sublinear. It's actually something like this, A, 1 over A. It's the inverse of linear. Okay. So first time to here, second time further. Is that correct? So this is the ratio of differences. This is the proportional differences between the throughput of the two. Yeah, I think so. And this is the other way around. Okay, so it's going to go bigger, bigger, bigger. So this is the differences of the x and y values, differences of x and y values. Okay, yes, I have to think about this more, but you get the idea. So if the starting point is here, it goes that way. Starting point here, it goes that way. But guys, if the starting point is here, if it's fair to begin with, it will remain fair. Okay. So this is MI, MD. Just come back the same way, right? What about AD? AD is just linearly coming back. It's going to drift further away if starting point is here. Similarly, it's come back, but drift further away. Okay. So they are actually diverging from being fair. Yeah?
Why there is a curve like exponential?
Okay, so I say exponential, but it might not be, sorry. But it's actually growing like this. Because this would up. You might be right. You know what? You are right. Yeah, so it's simply slope of A, and this is slope of 1 over A. But let's be careful, right? So this is, let's say this is connection 1 throughput, so T1, T2, and this is initial. Afterwards, we have 2T2 here and 2T1 here. And then 4T1 and 4T2, isn't it? Is this a straight line? Oh, yes, it is. And the slope is the initial throughput of 2/1. Okay, so if it's not fair to begin with, then it's not going to be fair. Okay, if it's fair to begin with, it's going to be fair. MIMD. What about MIAD? MIAD is definitely drifting away, and the slope is going to change. Well, actually, no, the slope is not going to change. The increasing slope is not going to change. No, it's still on the same slope, on the same straight line, except that it's decreasing a little bit slower, a constant. Well, you know, the same amount. Yeah, so it's going to change a little bit. So the second increase is going to be the new T2 divided by T1 after the decrease. Very good. I think you are, let me see. Nan Ce Sheng, right? Good. So are we converging? AIAD, is it going to reach fairness? Obviously not, right? No matter where you start, except that you are starting fair. MIMD, also not. MIAD actually drifting further away. So, nope. None of these will give you inter-TCP connection fairness. Neither of them will achieve, so yeah. Yuanxiang, none of them will achieve. Great. Okay, team 2 also come to the same thing. Everyone comfortable now? Are you still debating? Yeah, so the slope is essentially T2 divided by T1. Okay, so let's take a 10 minutes break and then come back to wrap up chapter 3. We have just one topic remaining. Hi.
May I ask a question?
Sure.
On the page that has some numbers, and I think
Is it the quiz page or?
It's a PowerPoint, a lecture.
Oh, the lecture? Okay, so let me close this. Here?
The previous page.
Oh, yes, this page. And I want to ask, is the number
How this value is calculated?
Oh, how is that value calculated? So CWND. Round trip time, 0.1 second. And this should give us 10 gigabits per second. And condition window size is the number of packets multiply, number of segments multiply MSS. And the MSS is 1500 bytes. Okay. So number of segments allowed in flight is then 1500 500B, a second, 10G BPS multiply 0.1 S. So this is 1 gigabits, and this is pi A.
Something like
Oh.
好像差不多是83333。okay, maybe it's because of the bytes. Yeah, 12,000. Yeah, 没有4 sorry. 8对。How embarrassing.
we just forget the bytes to multiply.
Yeah, I guess so. 所以这个除完以后应该差不多是 about A3. Good that you double checked. Yeah, so headache here. All right, good. You're welcome.
Only I want to ask this. Wait a minute.
Certainly. Not quite sure what's the question. And you're Yan'an, right?
I saw the different context in the video. Why?
So you asked a question when we're doing quiz 25?
Yeah.
Okay, certainly no more question. 再想想 what was
Why we have to multiply the maximum segment in here? In the quiz 23, we just use the format and plus the
plus 1 MSS
plus
plus 1
MSS.
Oopsie, sorry. Because I touched my microphone, it's gonna burst for the remote state. Yeah, so we actually add MSSM, multiply this value. And you use. Okay, so the goal there in congestion avoidance is to do additive increase, right? So you kind of increase the congestion window size by 1 per round trip time.
Yeah.
Okay.
Yeah.
And 1 is 1 MSS. Okay, so this is the goal. Okay.
Yeah.
The thing is that formula is applied when we receive an ACK. There could be multiple ACKs coming back in 1 round trip time. Say 4 ACKs. That is also saying for each ACK, we can only give it this much new window size. So the computation there is to find out, okay, how many new ones? Okay, how do I know if it's 1/4? Right, so it depends on how many ACKs there are. How many ACKs there will be within a window? It depends on the congestion window size divided by MSS, approximate, right? And sorry. So the number of ACKs is congestion window size divided by the maximum segment, by the segment size. Okay, and reverse it.
for each.
Yeah, this is the number of eggs. So this is the number of eggs in one round trip time.
Okay.
So for each egg, we increment this MSS. I know, because MSS seems to be a unit, and yet it's also a size.
Okay.
Okay, good.
Okay. Thank you.
All right, so good to know. Other questions? Okay. Where do I sign?
Here.
Right here. Good.
Thank you.
You're welcome. All right, so that's try to wrap up. So that was fairness in between TCP connections. So fairness can be extended to consider how TCP might be fair or not fair with UDP connections, for example, here. So many of the multimedia applications tend to not like TCP because TCP does congestion control. It's going to limit the transmission rate. So these multimedia applications might use UDP instead. They could be sending audio video in high rate, okay, sometimes constant rate, sometimes as high as possible. So UDP sending data this way is not going to be very fair to the TCP users. Okay. So in order to make UDP a little bit more fair to TCP, okay, people actually try to model TCP's average throughput. Okay, average throughput. So as you saw earlier, right? 3/4 of W over RTT. And ask UDP connections to send about that, okay, throughput. So depending on the round trip time between the multimedia application sender and receiver, plot that into the formula, okay, and come up with the fair rate, okay, for the TCP connection. Another is this, fairness between the applications starting TCP connections. Okay. The issue there is that after a while using TCP, some application designers or developers discovered that, hey, they could actually start parallel connections to speed things up. As you were working on PA7, you see that if you use Chrome to test, right, your PA7.go, you see that your PA7.go actually shows multiple entries of being asked for the file size. Okay, so this is very typically what the web browsers do. So let's consider this. Okay, why having parallel connections is not that fair. If we have a link in the middle, the rate is R. And there are already 9 applications, each starting 1 connection. Then each application and each TCP connection gets 1/9 of the rate. Okay. What if we start a new application, and this new application is asking for just 1 TCP? Then this new application, as well as this new TCP connection, gets only 10th of the R. But if we start the new application and starting 9 TCP connections in parallel, well, each TCP connection gets how much? 1/18 of R, right? But this application here gets how much? 1/2 of R. That is also why, not in all the protocol documents, but in the political body of ... okay, people actually do not advise browsers to start too many parallel connections. If I recall vaguely, last time I heard is that limited to 4, okay, and not more than 4. So if you see any browser starting more than 4, I think you can try to report those browsers. Okay, but similarly, okay, so it's actually, the enforcement is not very strict. It's more from peer pressure. Okay. So similarly to the UDP users, okay, it's up to the application designer of these multimedia applications to decide whether they limit their rate according to the TCP's formula. So you see a little bit that the internet is also a little bit political. Okay. Now, finally, we're done with TCP, which is this part on the left, taking the end-to-end approach to handle congestion. So we'll be guessing whether there's a congestion at the end. We'll be guessing also what is the good sending rate. Okay, and that's done by trying and failing, increasing window size, and decreasing window size in case we fail sending, okay, having packet drops. There's actually an alternative, if you recall, okay, in the overview of congestion control. It's called the network assisted approach. So instead of having the ends, okay, detecting there's congestion, routers, okay, so those machines inside the internet core will try to detect it by, for example, measuring if the free buffer space is too shallow. Okay. If that is the case, then the routers would actually mark some of the packets traveling through the router and use that as feedback to the end system. Okay. So for example, if the queue size is too long or the free buffer space is too shallow, mark those bits in the packets. Okay. So there's usually a single bit or maybe multiple bits in the packet, okay, in the IP layer header, in the network layer header. Okay. So in TCP IP, there's also additional bits, okay, at the transport layer to enable slowdown of the traffic accordingly. Okay. So essentially, using the network-assisted approach, routers tell explicitly, okay, there's a congestion, and oftentimes advise also what is the rate, okay, to adjust. How? Given the free buffer space, isn't it? So that will be the window size to recommend to the sender. So TCP, there's actually a special version of it that tries to do network-assisted congestion control. It's called the ECN. Explicit congestion notification, ECN. Okay, the way it works is this. In the packet, especially the IP header. So this is not the TCP header. This is the network layer header. So there are 2 bits, very special, in this field called TOS field, which we'll cover in chapter 4. Okay. So when the router detects that, the buffer is getting shallow, then those bits will be turned on. Okay. And packets will go through the internet, through these routers, to the receiver. Okay. So congestion indication is carried by these packets, like this. ECN bits, 2 of these bits, in the network layer header. As it travels through this hot router in the middle, a busy router in the middle, the bits get turned on, turned into 1, 1. And as this ECN packet arrives at the receiver, receiver sends this. A TCP-X segment with the ECE bit turned on, the E bits on. The sender side will get the ACK packet and then reduce the window size according to the recommendation. And then send back the CWR bit in the data packet going out next. So ECE, well, EC is the same. Explicit congestion notifications EC. EC, explicit congestion. And E here stands for echo, explicit congestion echoing from the receiver, okay, to the sender. Sender sends this, congestion window reduced, okay, message back to the receiver. And this CWR is kind of important because then receiver won't be sending more ECE, okay, later on. So CWR is to let the receiver know that, okay, no worries, I got you, I'm slowing down already. Okay. So this is a very special version of TCP, but don't worry, this is never used, okay, never used. Would you like to guess why? Okay, the hard part is down below here, the green packets. In order for these routers to mark the packets, that is actually extra effort. And these packets is going to go everywhere, okay? And the receiver is going to send a lot of these ECE, and the whole network will synchronously dropping the rate. It might not be that good either. And besides, so the free buffer space here is maybe X. Each receiver is going to tell the sender that, oh, this is the window space, the buffer space you are allowed to send. But other senders are also seeing that, right? How many senders are out there? You actually don't know, right? If all of us are sending that much data, it still overwhelms the router in the middle. So that router has some free space. But that router might be shared by many of the senders, many of the connections. And you don't know, you still don't know how many connections there are. So this ECN approach, although very ideal, but still, okay, a little bit far-fetched. So ENC, okay, E bit and C bit are actually here, okay, very nearby the other bits. The SYN bit, the FIN bit, and the other bits. So that was chapter 3. Okay. Major functionalities you see, multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Among them, RDT and congestion control, we spent a lot of time talking about. These are the top 10 problems. As you see, they are not that trivial, not like flow control or multiplexing, demultiplexing, quite straightforward. And so RDT and congestion control are also part of TCP. Therefore, we spend quite a bit of time on TCP. Starting now, we'll be leaving the edge of the internet and entering the core. Okay. So the next two chapters are actually separated this way. Both of them are actually network layer, but chapter 4 is about the data plane. Chapter 5, then the control plane. So chapter 4 and 5, very special because network layer is actually a little bit special as well. Let me come back and give you the chapter 4 slides, which is right here. All right. So the goal for this chapter is to focus on one of the major functionalities in the network layer, okay, which is this one here, forwarding. Okay. But in addition to talking about forwarding, to begin with, I need to give you an overview. So we'll be starting by talking about what is the functionality of the network layer in general, and what are ways of providing these functionalities. So there will be also some service models. Okay. Just like TCP and UDP, these are two different models, okay, supporting the functionalities necessary in transport layer. There are also alternative designs. Okay. But internet is one of the service models there. Okay. Two major functionalities in general, forwarding and routing. So forwarding is what chapter 4 is going to be focusing on. And I'm going to also give you an interview of how the router look like, the architecture of a router. But most of the content in chapter 4 is still going to be about, okay, the internet. So there are other type of networks, okay, used to compete with the internet, but implemented in a very different style, different model. Oh, you'll see. So let's go ahead and start. 4.1. So this is the network layer. Okay, what it does is simply this. Okay, the transport segments will be passed down to the network layer. Okay, so the network layer is there to receive these segments. Okay, and the network layer protocols is going to be in every host in order to receive these segments. But in addition to having them at the host, they are everywhere. Okay. So in addition to being at the hosts, they are everywhere on all the routers on the internet. Okay, so right here, all the routers. Okay. So on the sending side, let's say here, sender, and here, the receiver. The sender side is going to encapsulate the segments it receives, adding the network layer header and turn it into an even bigger packet called datagram. So you see that packet encapsulated, becoming big, and this datagram is going to be forwarded one hop at a time through all these routers. Okay, the way that routers find out a way to pass the segment is by examining the packet header. Okay. And so that allows the routers to decide how to pass it, and then eventually reaching the destination. Okay. So that packet is going to be received by the network layer of the receiver. The network layer header is going to be extracted, okay, removed, and then the remaining segment is going to be passed up to the transport layer. All right. So that's essentially how packet flows, okay, from the network layer's point of view. So there are two major functionalities. One is forwarding. So all it does is just what you observed in the animation, right? We are moving packets from one router to another router. And for one packet, you see that being done multiple times. In fact, there are lots of packets flowing, okay, as we speak. So forwarding, a really, really important functionality being used repeatedly. Okay. The other is routing. The second one here. This determines the routes, okay, the packet will take. Okay. Now, in order to do that, this is kind of an intelligent task. There's usually an algorithm, or a more precise routing algorithm, in order to calculate these routes. Okay. And the resulting routes will be installed into the routers, such that when packet arrives, okay, the router look at the result, route computation result, and determine quickly, okay, where the packet will go next, okay, which is the next router, okay, and so on and so forth. Now, if I use an analogy, okay, taking a trip. Let's suppose we are all taking a trip to the zoo, Taipei City Zoo. So what we usually do is what? Pull out our smartphone, isn't it? Right? And you open up Google Map, and then you type in zoo. Google Map is going to tell you what? Oh, you need to walk to some spot, right? And then take a bus right there at the stop. And the bus is going to take you to a stop nearby the zoo, and you take off, and then you walk into or go to the entrance of the zoo. Okay, so that process, finding a route there, is routing. Down here, the process of planning a trip, okay, finding out what to do before you start traveling is routing. So on the day of travel, okay, all you need to do is just, you open up the Google Map. The search results is probably still there. You just go to the next stop. At the stop, find out what is the route walking to the entrance. Okay, so that is forwarding. So routing is being done ahead of time so that on the day of travel, okay, everything is easy to do. Okay. You have already a rough idea. And in network layer, there are the separations of two planes, okay, the data plane and the control plane. So data plane is actually running local on each of the router. Okay, so this is a per router function. Okay. This is to determine for each datagram by looking at the header, what is the outgoing port? What is the next router? Because each of these port, okay, links to the next router. So there are actually 3 ports here in the example. Okay. And this is what's being looked at, the packet header fields that the router look at. Okay. So this is forwarding. So data plane is essentially handling the forwarding function. As opposed to control plane. Okay, this is the other one. What it does is way more complex because it's handling routing. Okay. So this is the network-wide logic. This is the algorithm computing all the routes in the network. Okay. So essentially determining how these datagrams would travel. Okay. What are the paths, okay, from one end to another end? So there are actually 2 approaches. The traditional routing algorithms, okay, will be implemented on each router. Okay, and each router will be doing this network-wide logic, and hopefully that they are consistent. Okay. The other approach, okay, the more modern approach is this: software-defined networking, SDN. Okay. Well, very different from the traditional approach, okay, where the algorithm is running on each of the routers. In SDN, the route computation is done only on high-end servers. Okay, for some network, there could be just one server there computing the routes for the entire network. For bigger network, bigger domain, there could be multiple ones, okay, to prevent failures. So that's a general idea. Let's focus on the data plane and speak more. In fact, chapter 4 is more on the data plane. How we do the routings, how the routings are being done in the traditional way versus the newer way. We'll also talk more in chapter 5. So right now, a little bit more about the data plane and a little bit more about the control plane. Okay, so as data arrives, okay, at the router, okay, this is per router data plane. So we'll be looking up a forwarding table. Okay, so forwarding table is essentially the key component to allow very, very fast identification of the output port. When I say output port, I also actually meant output interface. Port and interface, you will hear me using them interleavingly. So they are the same thing that I'm referring to. Okay. So data plane right here, down below. Sorry. So each of these is a router. Okay, the lower part is the data plane, okay, where we store these forwarding table. Given the header information finds the output port. So in this case, 0111 matches the third entry in the table, right? So we go to output interface 2 or output port 2. Okay, so down below the data plane. But the control plane up here is the one doing the route computation. In order to do route computation, these routers at the control plane will need to exchange information to each other. So the traditional one will be sending messages, short messages to each other in order to find out who's connected to who. So down below here at the data plane, we see, so this router here has 3 connections to other routers. And each of these other routers have also other connections to their neighboring routers. Okay. In order to find out the routes, the routers will need to know very well among each other the connectivity. So these exchanges of messages at the control plane is to acquire the information about the graph, about the network. So the network having routers interconnected with links, it's almost like a graph. Routers interconnected by the links, this is a graph. So with this graph, one can actually, with this graph, one can actually compute routes. For example, from this guy to this guy. This is very simple, so it's trivial. It can be a little bit more complex. So one can use routing algorithms to compute from A to B, what is the shortest path, for example. Okay. So this is what the traditional routers are doing. Okay. There's a separation of the data plane from control plane. Data plane doing very straightforward table lookup. That's called forwarding. Higher layer doing the logic computation. That's called the routing. Okay. So once the computation is done, that routes are installed back down to the data plane, and that forms the lookup table. But in modern days, the other model is software-defined networking. Okay, so only 1 or 2 servers are there to do the computation. So it looks a little bit different. Okay? In each of these local routers, the functionality is going to be very limited because it's not doing much of these control plane function. But the data plane there still needs a forwarding table. So somebody needs to do it. Okay, so there's a higher being up there. Okay. Oftentimes just 1 or 2 servers, maybe slightly more, 3, 4, okay, for a really large domain. But the thing is that, again, as I said, in the traditional model, one will need to know the connectivity from each other in order to come up with the routes. You need to have the graph. So there's some communication between the local routers to the higher beings, okay? The SDN, software-defined network, okay, servers, control plane servers. So communication happens between remote controller in the control plane server, to the CAs, the control agents, okay, in the routers. So CAs in the routers tell the remote controller the connectivities of themselves to the neighboring routers. And the remote controller, we generate the graph according to these reports and then compute routes. As a result, the routes are installed back to the data plane. That's how the local routers can still perform forwarding function. Okay. But in either case, traditional or the centralized or the newer one, SDN, the forwarding function remain the same. Packet come, packet header field, look up a forwarding table and determine who's the next network interface to go out. So only in chapter 5, you will see there will be two different parts. Traditional internet control plane works this way, and then SDN works another way. The last bit of 4.1 is this. Hey, we said that we want to talk about the service models. So this part is going to be very general. Okay? Two functionalities, routing, forwarding, very general for all networks. But you see in internet probably that the forwarding is done based on the destination IP address more today. And two data planes, this is actually more specific to internet, where we have forwarding at the lower level and then control at the higher level. Service model is going to be very general again. Okay? Just like routing, forwarding, these are very basic functionalities in every network. Okay. Now, the reason that I bring this up is the memory is still fresh. Remember this? And the reason that we need TCP is because the underlying channel is unreliable. Okay? And the transport layer services, we could actually provide two different model of services, right? UDP or TCP, reliable or not reliable. Similarly, at the network layer, we can try to provide services also in different service models with different levels of quality. First is called the connectionless network layer service. Okay. Hey, UDP, how do we call UDP not being reliable? Best effort. So the network layer that is connectionless is also a best effort service. Okay. In fact, internet is running in this model, the connectionless service model. So the two end hosts, including all the routers in the middle, there's no connection being set up ahead of time. So data will just go. Okay. Data doesn't need to wait until having a connection being set up like circuit switching. They just go. Okay. This is also why internet is packet switching, not circuit switching. Now the other one is then circuit switching. Okay, or the other way around to call it connection-oriented service. Okay. Now, internet is definitely not this, but there used to be some networks, ATM, frame relay, X25. They're designed and implemented to some degree, taking this model. So the other way around then, before data can go, the two hosts, as well as the routers in the middle, need to set up a connection, needs to establish a connection first. So routers involved, before setting up something. Right? So just be very careful. I'm saying TCP being connection-oriented and ATM being connection-oriented. Okay, but the connection actually are established at different levels. Okay, for the network layer protocols, when I meant connection-oriented, I meant the two hosts, including the routers. There's a connection set up. But at the transport layer, when I say connection-oriented, TCP being a connection-oriented protocol means two processes are connected, by the port number. Remember? Okay. So even though they are characterized the same way, connection-oriented or connectionless, but that connection is actually at very different levels. Process to process versus host to host. All right. Now, even within, for example, connection-oriented network, okay, one can set up services at different granularity. Okay. So for example, if we are establishing a connection or establish a channel, we can try to design the transfer of the data such that it guarantees different things. For example, one can guarantee the transmission of individual datagrams. Okay, so for example, we can guarantee that the datagram will arrive. Or we could try to guarantee that the datagram will arrive within a time duration, for example, 40 milliseconds. We can also try to devise a network such that we can guarantee this, or set up a circuit and guarantee this. A train of these packets, for example, will arrive in order. Or this train of packet will be guaranteed a specific amount of bandwidth. Okay. Or the delay between these packets in the train, okay, will be kept constant. Okay. For multimedia content, that is actually a really nice property to have. Okay. And that's why you see here, this is kind of a table giving you some examples. Internet at the top, okay, is best effort. There's no way of guaranteeing anything further in finite granularity, so up here. So there's no guarantee, no bandwidth guarantee, no loss guarantee, no packeting order guarantee, no delay guarantee, nothing. Okay, best effort. But ATM being a connection-oriented network service, it actually provides different levels: CBR, VBR, ABR, UBR, 4 different levels of services. CBR, very straightforward, constant bitrate service. So in this service, we guarantee some bandwidth, that constant bitrate. Okay. Do we guarantee loss? Well, if the data is within that constant bitrate, yes. Packet will definitely arrive in order because there's a circuit built. Therefore, you see in ATM, packets will always arrive in order. Okay. Timings, yes, if the data transmission is within this constant bit rate, okay, and there's no congestion. Now, if the data itself is variable bit rate and asking for a VBR service, what it does is to guarantee to the maximum bit rate. So it's going to guarantee the maximum bit rate. Okay? So bandwidth is guaranteed, and everything else is also guaranteed. So you see that VBR is very, very resource consuming, okay, relative to CBR. ABR is available bit rate. It's like saying I guaranteed you to some minimum level. If you want to send data beyond this level, we're not sure. We cannot guarantee anymore. Okay, so it's guaranteeing, but only to a minimum bandwidth. So there could be loss, sorry. In order, yes. Timing, not sure, because there could be loss. So timing is not guaranteed either. Okay. But we'll give you condition feedback. Okay. Last is the UBR. So this is the unit bit rate. Okay, so this is like saying something really close to best effort, except that packet in order arrival will be guaranteed. Okay, no bandwidth, no loss, no timing guarantee. All right. Okay, so 4.1, just like all the overall overview sections. Sorry, it might sound a little bit boring and fuzzy because these are all very high-level terms. Okay, to take as takeaway here, 2 functions, routing, forwarding, 2 planes, control and data, and 1 kind of corresponds to each of the function. Service model, you just remember internet is connectionless. okay, because the connection-oriented one no longer exists. And we move to 4.2. What does the router look like? This is then a lot more interesting. So this is the overall building boxes of the components in a router. So first you see is this thing at the top, routing processor. That is the box running the routing algorithm. So it's drawn higher, so it's kind of control plane, clear. And therefore, all these down below, all these big box with three small boxes, each of them is called the router input port, is in the data plane. Switching fabric, also data plane. So is router output ports. So processor here, after computing routes, will install forwarding table into these router input ports. So specifically, the red boxes here in the input port. So those are the forwarding tables. So here that's zooming into each of these input ports. The three smaller boxes are these. Line termination, link layer protocol, and then here, the lookup, forwarding table lookup. So line termination here is essentially taking the electromagnetic waves, restore the 0 or 1 bits out of the waves. So those are the modulators and demodulators. For input port, it's essentially demodulator, taking the 0, 1 bits out of the waves. With the 0 and 1s, then we put the 0, 1 bits within a frame up to the link layer. So some of these link layer protocols would also do error check, bit error check, as well as in case there's error, recovering from the bit errors. But those are in the data link layer protocols. That's even lower, so below the network layer. So for example, Ethernet or Wi-Fi, those are in Chapter 6, which we will not be able to talk about at all. So essentially, frame arrive here at the link layer, and then the link layer header removed, and then the datagram gets passed here into this box. So this is the real input port queue. So what it does there is very straightforward, just table lookup. Table lookup is exactly what we are doing in forwarding, the first major functionality there. So what you see there is this box is going to check this thing, using the header field values, and match the entries in the table and find out where the output ports are. So again, forwarding. So forwarding equals trying to find a match and determine what port to go. So the goal here, a little bit tricky, is to complete the matching in the line speed. By line speed, I actually meant here, this line here. If the lookup process here is slow and this is fast, what's going to happen here is, some of these packets will need to wait in the queue for the matching to complete. So this is the first part in the router that queuing delay can be observed. If the datagram arrives faster, but the switching fabric is not fast enough to pass the packets, or if the lookup process is not fast enough, packets get queued up. As to what header field we look at, traditional forwarding looks at the destination IP address, and that's it. But the more general forwarding, SDN, could be looking at multiple header fields. So this is the traditional forwarding based on IP address, particularly the destination IP address. So what we do is just to grab a packet header IP address field and match. Try to match one of these entries. So the numbers on the left are all destination IP addresses. IP address is 16 bits long, right? So 4 of these 8 bits, 32 bits long, okay? So in case we find a match, okay, in this range, then go to link interface 0. If we match this range, 1 and 2 and 3. So it's quite straightforward. But if we have one destination IP address per entry, how many entries there could be? Worst case, this many. So the table is going to be too large. So the way we handle this is actually doing it this way. Instead of writing the IP addresses out in full, we use these things, prefix. So they are called the address prefix. If we go back one slide, observe, okay, all these IP addresses in the first range, how many bits are in common? Well, you see the first octet, identical. Second octet, identical. Third octet, match to where? Only the first 5 bits match. So you see down here, first 2 octets, third octets match to the first 5 bits, and all the rest, wildcards. Okay, so that is saying if the destination IP address match to this pattern, and I'm going to leave the last 8 plus 3, 11 bits flexible. It's okay. If those values are not quite the same, it's okay. It still match this prefix. Okay. So if we match to the first prefix, we go to interface 0. Match to the second prefix to interface 1. You'll see if we go back one slide. You see here? Yeah, the IP addresses of the range number 2, first 24 bits are the same. Only the last 8 bits are different. That's why the prefix looks like this. Okay. So we write the numbers that are in common, okay, in the range. Okay, let's just exercise 2 cases, and then we'll call it a day. So let's see. If there's a packet coming in with the destination address looking like this, 1100, 1000, and so on and so forth. So which of these prefixes you find this IP address match to? Does it match range 1? Prefix 1. Oh, it does, right? 00010. Nice. Does it match range number 2, prefix number 2? Okay, okay, Shiwei is already saying, yeah, going to link interface 0. Okay, because it doesn't match prefix 2 either, right? It doesn't match prefix 3 either. So obviously, we go to link interface 0. But what about this case? It doesn't match prefix number 1. Does it match prefix number 2? It does. 11000. Does it match prefix 3? Wait a minute. It matches also prefix 3. In this case, which interface do we choose? Well, the router's forwarding function is doing this. It's not just prefix match. So it's not just prefix matching, it's also longest prefix matching. Which one is longer? Number 2, right? So interface should be, yeah. Okay, 1. So that's the idea. The forwarding table lookup, the forwarding table actually looks like this, right here. Having prefixes and outgoing interfaces. Okay, and lookup is to do essentially longest prefix matching. And that's all for today. I'll see you Thursday, okay, for the exam. By the way, Wu Junting looked familiar. His student ID is somewhat left here, okay, on the desk somewhere. So would you pick it up for him? All right, so that's it, guys. I'm just gonna stop the stream.